Okay, now we're going to talk about the two different types of nuclear energy. You have a whole thing of notes there. I'm going to go through some of these pretty quickly because you can read through these, but I'll highlight some things. Okay, first of all, we have nuclear fission. This is one type that is pretty important, and it's just the splitting of heavier isotopes into lighter isotopes. And in the process, we get a whole bunch of energy that's released. And by a whole bunch, we're talking somewhere around 1,000,000 times more than with chemical reactions. So it's a huge release of energy. And you can have chain reactions. And with chain reactions, this is when you have something like uranium-235. That's one isotope that can undergo a chain reaction. And it is bombarded by a neutron, a slow neutron, and it needs to be slow in order for this to occur. That'll make sense later on when I talk about something else. But we have this slow neutron that hits this isotope, this heavy isotope of something like uranium-235, and that uranium-235 splits into two lighter weight, really medium weight isotopes, and in the process it spits out 3 additional neutrons. Those neutrons then go to hit more of that fissile material, more of that uranium-235, and that process just keeps continuing. And here's an example of that reaction. You do not need to know this exact reaction, but again, you have a slow neutron, hits your uranium-235. In the process, it creates, forms 2 medium weight isotopes, usually krypton and barium. It might be different isotopes of krypton and barium, but it doesn't really matter. Don't worry about knowing those. But in the process, you get those 3 neutrons that are also emitted. And there are only certain isotopes that can undergo fission. Uranium-235 is a very common one. You can also get uranium-233 or plutonium-239. And an uncontrolled chain reaction is also known as a bomb. So really it's just when you have enough mass that chain reaction keeps going and going very rapidly, and in the process it just creates those huge amounts of energy. So a couple very famous bombs that you might want to know about are Little Boy and Fat Man. And with Little Boy, this was used in Hiroshima, and the process was that it was a cylinder. It was about 10 feet long, and in the center here was some TNT, an explosive device here, and then in little semicircles around the sides we had some uranium-235, and that uranium-235 was a subcritical mass. Each of those hemispheres or semicircles are subcritical masses of uranium-235. So that when this explosion, when the TNT went off, those two masses came together and created a critical mass of the uranium-235, and so a chain reaction then took place. That bombed just very rapidly. And the other one we have is Fat Man. And in this situation, you've got this, it's a little bit more cylindrical or spherical, and it's about 5 feet in diameter. And the process here is that we have a lot of subcritical masses of, let's say, subcritical mass, and I believe it was plutonium-239 in this case. And then there was an implosion, something that caused basically all of these subcritical masses to come in towards the center. And so again, when you got them all coming in towards the center, you get that critical mass. So that's how this ends up working. It's an implosion on this one. So you can Google that type of stuff and get a little bit more background if you'd like, and there's videos and such you can see. Okay, then we have our controlled chain reactions, and the way we see these are in nuclear reactors, and there are different parts to the nuclear reactor that you should be familiar with. And again, you can read these in your book and in your notes, but I will hit a couple of the important things. Fuel rods, that's just going to be your radioactive isotopes. It's going to be your uranium-235 or plutonium-239. A moderator is used to slow down neutrons. So we said earlier that you need to have those neutrons moving really slowly in order to bombard that uranium-235. So that's what a moderator does, is it's used to slow down neutrons. And by doing so, it actually speeds up the reaction, speeds reaction up. So what this does, the neutrons it slows down the collisions, and it makes this reaction actually occur quicker by doing this, having a moderator in there. The control rods are used to absorb the neutrons, and by absorbing the neutrons, that slows down the reaction. That's different than your moderator. And it's kind of like putting brakes on the reactor. And then we have the containment vessel, which is this structure right here that you can see on your diagram. It's typically going to be dome-shaped or spherically shaped, because that's going to be very strong to have it like that. And then you've also got coolant, and it's the material inside the reactor. It carries the heat of the reaction through pipes to a source of water, which boils and drives the steam turbines. And you don't have this in your notes. I'm not going to spend too much time on this, but we could talk about nuclear waste as well, and where some of this stuff is stored, as well as some different accidents that have happened, but most of these have been due to human error. Okay, that takes us to our second one, which is fusion. And with fusion, here we have a process where you have two lightweight nuclei that combine to form a heavier one. And typically what we're looking at here is an isotope, is just two isotopes of hydrogen. So if it's hydrogen, it has an atomic number of 1, but we have hydrogen 2 and hydrogen 3, also known as deuterium and tritium. And when those are combined, we get, this should look familiar, an alpha particle. You get helium plus a neutron that's emitted. And this is the process that we expect, or that we know occurs on the sun, and let's see, and produces a lot of energy. In fact, it produces great amount of energy, and it's preferable, if we were to think about the byproducts and stuff, it's a preferable process because there's no radioactive byproducts and it produces more energy. However, it's not feasible for us to carry this out on a large scale, and mainly because it has to be carried out at really high temperatures, and we don't have any sort of material to contain that. So, and it also has to be carried out in a plasma, so we don't have a way to actually make that happen yet. And a couple of reasons to continue research, and that's really about it. So I would advise you to just kind of skim through your book, look through your book on these notes as well.